Hello everyone, we are going to study continuation of fluid kinematics. In this session, we are going to solve some numerical problems on velocity and acceleration components. You will appreciate that it is more dependent on a bit of differentiation of your mathematics. We'll see straight away uh, fluid kinematics fundamentals first. We'll revise the things and then afterwards we'll switch over to problems. Okay, and this is already studied. The motion of fluid is characterized by the velocity of flow. The flow characteristics can be, it can be velocity, can be density, can be pressure at the point of consideration in the flow, right? Any one of them, but in general we hold it as velocity and discuss the whole matter. So as fluid particle moves in space, its velocity depends upon x, y, z and t. So even the pressure depends upon x, y, z and t. The density depends upon x, y, z and t. Okay, that is velocity component in x direction. That is rather than calling it as vx, vy, vz, we have indicated it as u, v, w. Last time we have seen. So u is a function of x, y, z and t. V is a function of x, y, z and t. W is function of x, y, z and t. So for three-dimensional flow, if it is a two-dimensional flow, one of these axes gets omitted and then only remaining x, y and t will be coming. Likewise, it can reduce up to unidirectional or one-dimensional flow. Okay, and then okay, this is the problem number one. Here what is that is given is for a 3D flow. So for 3D flow means you have xyz or xyz. Now total velocity, capital V indicates total velocity, is equal to y squared plus z squared I plus x squared plus z squared z plus x squared plus y squared k. Now you can appreciate that this is nothing but equal to, if you remember, this is ui, okay, then you got plus in between. This is nothing but v because there is a j here, and then plus because there is a k here, this is w, that is velocity component in z direction. Okay, u is equal to y squared plus z squared, phi is equal to x squared plus z squared, and w is equal to x squared plus y squared. That's how it is. Okay, so total velocity is given in terms of components. Now what is asked is find at a point 1, 2, 3, right? Find at a point 1, 2, 3 the components of acceleration and rotation. So it is asked components of acceleration as well as rotation. Acceleration components are ax, ay, az. Rotational components are omega 1, omega 2, omega 3, or omega x, omega y, omega z. Okay, this is the problem given up to this. Now the solution starts. In solution, what I write here is, from the given data I can write here u is equal to y squared plus z squared, phi is equal to x squared plus z squared, omega equal to x squared plus y squared. Now if you recall, x component of acceleration ax is equal to dou u by dou t plus of course u into dou u by dou x plus v into dou u by dou y plus omega into dou u by dou z. That's how the components are. But here as v is not a function of time, right, or u is not a function of time, so to say, dou u by dou t is equal to 0. U is given here, dou u by dou x, there is no x term, it is equal to 0. Dou u by dou y, it is 2y, and then again dou u by dou z is 2z. So because I know u as this, I can work out all these components. So these components are worked out by using this information. Okay, because u is known and we want a differentiation of u only with respect to t, with respect to x, with respect to y, with respect to z. Now in this case there is a term rho, but here there is no term rho, or it is considered as incompressible flow, so there is no rho as such. Okay. Now similarly, if I work out other things also required and then write down, now what should I write? Ax is equal to, first term is 0, and then second term u into dou u by dou x. U is this, u is y squared plus okay, dou u by dou x has come up to be 0, that is not there, so first term is fully gone. Then you will be having x squared plus z squared, so this is straight away coming here. These terms are zeros, so x squared plus z squared into what, v into dou u by dou y. So v is there, dou u by dou y is 2y plus omega, that is x squared plus y squared omega, then dou u by dou z, or dou u by dou z is 2z. Okay, now I have substituted in this equation, but here this is 0 and this is also 0, that's why v has come here. So this term is v, this term is dou u by dou y, this term is omega, this term is dou u by dou z. So if you simplify after substitution of x, y, z values as 1, 2, 3, so this is 3 squared plus 1 squared, 2 into y is 2, 1 squared plus 2 squared, 2 into 3. So the whole thing turns out to be 40 plus 30, that's equal to 70 units. It is acceleration, so if you want to attach the terms as meters and seconds, it will be meter per second squared. So 70 units of acceleration in x direction. On the same lines we'll work out for y also. Okay, here when I write ay is differentiation with respect to t of v is this, so this is nothing but v plus terms are u into dou v by dou x, phi into dou v by dou y, omega into dou v by dou z. So u I have y squared plus z squared, dou v by dou x is 2x written here, plus dou v by dou y, so differentiation of v with respect to y leads to 0, right, so that is 0. Omega is x squared plus y squared, and dou v by dou z, so differentiation of this term with respect to z to z or to z. Now the whole term after substitution of x equal to 1, y equal to 2, 3 equal to 3 turns out to be like this, reduces to 56 units. Az, the component of acceleration a in terms, in the direction of z, dou omega by dou t plus you have UVW, and then differentiation of omega itself with respect to x, y, and then z. Omega is not function of time. You can just see here, this is omega, this is omega, so it is not function of time. U is y squared plus z squared, dou by dou x of omega, yeah, it is 2x, fine. V is x squared plus z squared, d dou by dou y of omega, that is 2y, plus omega is fine, but dou omega by dou z is equal to 0, so this leads to a 0 quantity there. Now again, putting x equal to 1, y equal to 2, and z equal to 3, I'll get this value, then it will be 66 units. So earlier slide has 70 units, AX, 70, 56, 66. If you want total acceleration, okay, that is capital A if you want. So how do I write this? 76I plus this is 56Z these are acceleration components, 66K. So this is how acceleration will be. Or if you want magnitude of acceleration, that is modulus of A, you know that it is square root of 76 squared plus you will have 56 squared plus this 66 squared. Now when you work out, you will be getting some magnitude that will be called as total acceleration of so many units, or you can say it is meter per second squared as the units of measurement. Okay, that's how acceleration is worked out given the expression for velocity of flow. Okay, now rotation, they have asked rotational components. These are rotational components. Again, this is U, you know that this is V, this is omega. Okay, now how to write omega x? I have told you, if you remember, omega x is written as half into bracket, there is minus term already, but in the denominator we will be having continuation of x as y, and then z, actually dou y by dou z it should be. So compared to z you have dou w, compared to dou y you will be having dou v. So half into bracket differentiation of omega with respect to y, that is 2y, that's there, minus differentiation of v with respect to z, that is minus 2z, fine, that's equal to half into bracket y is equal to 2, that's why it is 4, z is equal to 3 minus 6, overall it reduces to minus 1, it is omega rotation, that's why it will be minus 1 radians per second. Similarly, omega y half dou z dou x dou u dou w and half into bracket 2z minus differentiation of omega with respect to x is 2x, then substitution leads to 2 radians per second. Similarly, omega z equal to half into bracket dou v by dou x dou y v u s dou v by dou x is 2x, dou u by dou y is 2y, Simplification gives you half 2 minus 4, that is minus 1 radians per second. So these are rotational components in different directions. So that completes the problem number 1. We'll go to the next. Okay, here I have revised slightly laminar flow. Slight discussion on this, and then again we'll jump over back to problems. Okay, a laminar flow, in this fluid particles move in layers, one layer over the another layer, like a systematic parade. Viscous forces are predominant in laminar flows, you know this. Turbulent flow, in this the fluid particles move haphazardly. This results in a rapid continuous mixing of fluids. Eddies of different size and shapes are formed. Here both velocity and pressure fluctuate a lot. Okay, that's why this is called turbulent flow. Nothing is fixed as such. Okay, layer wise uniform motion will not be there. It will be intermixing of the particles will be there. Now comparison of laminar flow and turbulent flow. So here I would like to write an expression for Reynolds number. Of course you are going to study in dynamics the same thing, but to make a comment on these two flows, you should know the expression. Last time I had given you, it is Vd rho by mu. If you remember that expression, Reynolds number is given by V d rho by mu. Rho is density, mu is viscosity, dynamic viscosity, d is the diameter of the pipe, then v is the velocity of the flow. How this comes is Reynolds number is defined as it is a ratio of forces. Now what forces it will be having? It will be having viscous forces in the numerator, viscous forces in the numerator, and then in the denominator it will be having inertia forces. You will know afterwards that all these numbers that we define in fluid mechanics will be having denominator as inertia force only, because it will be there in all the problems of analysis, because whenever there is a mass there is an existence of inertia. So this denominator is fixed, inertia force is fixed in the denominator. Only in the numerator variety of forces come. If viscous force comes into picture, this number or this ratio is called as Reynolds number. Suppose there is a gravitational force on the top and then inertia force on the bottom, then such a combination is called as Fruit's number, gravitational force divided by inertia force. Likewise, we are going to define there are so many other dimensionless numbers. Now if you know this as well as if you know this, you will be able to make comment like this. Let's say sheet-like flow, as far as laminar flow is concerned, intermixing of particles or layers, and then haphazard flow as well as turbulent flow is concerned. Now laminar flow, look at this. If the laminar flow is there, the velocity has to be less. So velocity of the flow is mild, and larger the velocity of the flow, turbulent flow it will be. So as the velocity increases, it will be becoming turbulent flow. Now as velocity is less, obviously the discharge will be less. If the velocity is more, discharge will be more. Then at the boundary the disturbance is less. When there is a pipe flow, there is a flow along the periphery, and then if there is a open channel flow, again there is a flow on the sides as well as the bottom, which will be touching the surface of canal or pipe, where there will be a lot of disturbance. But in case of laminar flow, at the boundary the disturbance is quite less. but in case of turbulent flow, the disturbance is very high at the boundary. Next is viscous forces predominate, hence Reynolds number is less in magnitude. In case of laminar flow, you have seen that it is less than 2000. If the number, if the ratio value is becoming more than 4000, then we'll classify it as turbulent flow. And between 2000 and 4000, of course, it will be neither laminar nor turbulent. That's why it is called a transition flow or flow under transition, right? If the number is less than 2000, then it is a laminar flow where viscous forces will be more, right? And inertia forces are less predominant. And then if in turbulent flow, what happens is these forces become too much and inertia force becomes less. That's why this ratio becomes too high. Okay, we'll see further. Now examples of flow. Okay, here you should understand and try to imagine the situations. Flow through constant diameter pipe attached to a constant head tank. It is like this. Almost all the cases are like this only. The pipe is constant diameter, it is not changing like this. And not only that, the head over the pipe is also constant. Something is happening and then maybe it is getting recharged, but as the flow is occurring, this is not coming down. That's what is said. Flow through constant diameter pipe, that is first part. Constant diameter pipe attached to constant head tank. Here there is a head and this is also constant, means the head H which is acting on the pipe is fixed. As this is fixed, the pressure with which the water is pushed out is also fixed, and as the diameter is same, the velocity of the flow has to be same everywhere. So what will be the flow? With respect to time, it is not changing. With respect to space also, it is not changing. That's why this is steady and uniform flow. Steady because with respect to time, the head is not changing. Because of that, the velocities are not changing. It's a constant diameter. So whatever velocity at one point is there, the same velocity will be there on the other point. So that's why it is steady as well as uniform flow. Second case, flow through tapering pipe attached to a constant head tank. So exactly similar situation, but only thing is here the diameter of the pipe is continuously decreasing. This head is not changing, head is remaining the same. Okay, now what happens is here when the diameter is large, the velocity will be there, but as the flow occurs, the cross section, when it becomes larger, the velocity becomes more because same discharge has to move on. So velocities at different points, if you observe, they are changing, but as this head is constant, whatever velocity that is there here will be the same there. With respect to time, it is not changing, but with respect to space, it is changing. That's why in the second case, it is non-uniform flow, but it is a steady flow. With respect to the time, there is no variation. So it is a case like that. The first one is case like this. Okay, so this is steady as well as uniform. This is steady but non-uniform flow. Okay, we'll see the third one. Flow through constant diameter pipe attached to a tank with varying head. Okay, here the same thing, constant diameter pipe, but this is continuously changing. Means with respect to time, if you take, the change is occurring. Now while occurring at from some instant of time, if you consider some instant of time, whatever velocity was there here, with the same velocity will be there next section also, right, at the same instant. Because of that it is uniform, but as the time passes, the head is decreasing, the velocities will be continuously changing. What I mean is, suppose in the beginning there is 10 meters high, here it will be 5 meter per second, let us say. Here should also it be 5 meter per second, because it is a constant diameter pipe. Now once it becomes 8 meters, the velocity will be obviously reduced, but whatever velocity that will be reduced, maybe it is now 4 meter per second, this should also be 4 meter per second. In the sense, with respect to space there is no change, but with respect to time there is going to be a change. Hence this particular flow in third case, where varying head is there, constant diameter is there, it will be non-steady or unsteady flow, but it is a uniform flow, unsteady but uniform flow. Case number 4, flow through tapering pipe attached to a tank with varying head. Yeah, tapering pipe, varying head, in the sense it is both unsteady as well as non-uniform. With respect to time also it changes, with respect to space points also there will be change. So it will be unsteady and non-uniform flow. Flow through a long pipe, just a long pipe, obviously it will be uniform flow and then steady flow. Flow through a base of the dam, flow through base of the dam, it will be 2D flow. Generally whenever there is a dam, right, and then dam means there will be water standing, and this standing water will be getting penetrated into the ground, and then gradually it moves and it moves out, right. Another point it goes and then goes up like that. So like that the flow will be occurring. We'll be studying in detail. This is called flow net or streamlines, right. So this flows at the bottom like that. There won't be any flow perpendicular to the plane of the board or perpendicular plane of the paper. In such case it is a 2D flow. Flow towards tube well from an aquifer. Yeah, this is a 3D flow, because when you have a tube well, okay, tube penetrating into the ground, okay. Now whenever there is a water surface surrounding this pipe, so whenever pipe water is taken out, there will be a drop of velocity, surface of water from all around, as if it will be going down like that, contributing for the discharge, charging of the well. So this is obviously a 3D flow. Okay. Number 8, here there is a flow, there are points A and B, and they have said in case A, at time 8 am, velocity at A is 8 meter per second, velocity at B is 12 meter per second. At time t 8:15 am, means after 15 minutes, velocity at A is 8 meter per second, but velocity of B will be still 1 meter per second or 12 meter per second. So here with respect to time there is no change, that's why it is steady first of all. But with respect to space there is a change, that's why it is non-uniform. So it is steady but non-uniform. Second case, case B, at t is equal to 10 am, VA is 8, VB is 8. At t is equal to 10:15, VA is 15, VB is also 15. Now with respect to time, if you see, there is a change. So unsteady flow it is, first part, right? And then it is at A at a particular instant of time is 8, B is also 8. Like that, even if you change the time, it is VA is 15 meter per second, VB is also 15 meter per second. Again it is uniform. right? The same values will be there. So it is unsteady, but it is uniform flow. U, that is unsteady but uniform flow. You should not use the abbreviations, you should write full words. Take care. Okay, this is a problem from the question paper, earlier question paper. I have solved it for you. We'll see here how it will be. The boxed material is a question part. So whatever red boxes I have put, that's a question. The thing which is written out of box is a solution, obviously. In each of the following case studies, giving reasons whether the flow is steady, unsteady, uniform, that's what you have to classify. So first one is u equal to 10xt plus 15x squared. That's an expression. Now the u means what? Velocity of x component. X is a space point, t is a time. Now only it depends upon x component, because of that it is unidirectional, right? It is dependent on time, because of that it is unsteady. Unsteady flow, right? You cannot change whether uniform or non-uniform. It is dependent on time, that's why I can tell that it is unsteady. And as the space point changes, x equal to 1 if you put, x equal to 2, 3 if you put, go on putting the values, the expression u will be getting different values. So velocity is dependent on space as well as time. So a fluid characteristics or velocity changes with respect to time and also space, hence it is unsteady and non-uniform flow. That's why, if this is the expression. Now suppose u is equal to 20, it is given. What happens is, with respect to time also it is not changing. There is no t term, there is no x term also to tell that it is space dependent. So no change with respect to time and space, hence it is both steady and uniform. The third case, flow in bent pipe with constant discharge. Bent pipe, constant discharge, right? Uniform pipe we shall assume. Because of that the velocity direction is changing. Means what? Velocity is changing, magnitude is not changing. So change is with respect to space, but not with respect to time, hence it is a steady but not non-uniform. Flow in converging pipe in which discharge is gradually increased. Flow in converging pipe in which discharge is gradually increased. So it is time dependent but not space dependent. So characteristics change with respect to time and space, hence it is unsteady and non-uniform, right? So gradually there is a change. That's why time is, as time passes it is unsteady. Space wise also there is a variation, that's why it is non-uniform flow. Now flow in a constant diameter pipe in which discharge is continuously increasing. Flow in a constant diameter pipe in which the discharge is continuously increasing. The velocity increases with respect to time, but it will be uniform space wise. So the flow characteristic velocity changes with respect to time, but with respect to space there is no change, hence it is uniform but unsteady flow. Okay, with this I think